Dear students, today we are going to discuss on the topic photochemistry. When light is used as a form of energy, two main processes are involved. The first one is photophysical process and the second one is photochemical process. So, let us just take a glance at what is the difference between photophysical process and a photochemical process. So, concerning on the photophysical process, you have a molecule that is A and you are radiating the molecule with a source of energy that is in the form of light, that is h nu, and it gets converted into an excited state, that is A star. Within a very short span of time, it returns back to the original state, that is to the A. That is basically here there is no kind of chemical reaction or bond breaking is happening in this particular process. So, whatever you are getting as a product, it's the same thing as that you have got as the reactant. So, basically no new product is formed in this process. So, basically when we concern about photophysical process, it is basically a change in the physical state or a change in the spin of the molecule would be happening in this process. Now, next process is photochemical process. In a photochemical process, you have a molecule that is A. You are irradiating with a suitable light, that is h nu. It gets converted into an excited state A star, and after which it converts into the product form, that is P. So, basically you have a particular compound, that is A or the molecule A, and after the reaction or after the photochemical process, you are basically getting the product, that is P. So, this is the main difference between the photophysical process and the photochemical process. In a photophysical process, you are basically getting the same molecule in the end or as the product, but in the photochemical process you are getting a different product in the end of this reaction. Now that we have understood the difference between the photophysical and the photochemical process, we are going to understand why light is used as a form of radiation or light is used as a form of energy over the thermal energy. When thermal energy is used as a source, there is no selectivity of the product. If we assume that we need to get this particular product from this reaction, that is not mainly achievable using the thermal energy. So, there is no selectivity of the product. But whereas when we use light as a source, there is basically selectivity of the product. So, when chemistry is concerned, everything revolves around an electron. So, before moving on to the most important portions of the photochemistry, that is the Jablonski diagram, we have to understand how the electrons are paired and what are the spin of these electrons. So, when we have two electrons, the electrons can be occupied in many different orientations. Either one of the electron can be faced in the upward direction, the other can be faced in the downward direction, or both the electrons can be faced in the upward direction, or both the electrons can be occupied in the downward direction. So, when one of the electron is facing in the upward direction, its spin ms is equal to plus half, and whereas when the electron is occupied in the downward direction, its spin, or it can say that the spin quantum number is minus half. So, when you are taking this particular orientation, the total spin can be calculated as ms1 plus ms2. So, that is plus half and plus of minus half. So, that is basically 0. So, the total spin of this orientation is found out to be 0. And now, let us take another factor, that is the spin multiplicity. The spin multiplicity can be calculated with an equation, multiplicity, so that is 2s plus 1. Now, substituting this value, that is the s value for this orientation is 0, and when we are substituting this 2 into 0 plus 1, that turns out to be 1, and therefore, this orientation is called as the singlet state. So, it is just for this orientation, the total spin is found out to be 0, and when we are substituting it in the spin multiplicity formula, that is 2s plus 1, we get the value as 1, and therefore, this orientation or this state correspond to the singlet state. So, the next two orientation of the electrons is, the first one is both the electrons are facing in the upward direction, and the next one is both the electrons are facing in the downward direction. So, when both the electrons are facing in the upward direction, the total spin of this electron is found out to be half, that is plus half plus half, that is found out to be 1, whereas in this case the ms1 plus ms2 is found out to be minus half plus minus half, and that is found out to be minus 1. So, basically when you are taking the spin multiplicity of these two orientation, that is in this case the 2s plus 1 is found out to be 2 into 1 plus 1, that is equal to 3, and in this case we are taking the modulus, that is we assume that the spin, the total spin of the electrons to be not having a negative quantity, and therefore we take the modulus, and therefore in this case the total spin multiplicity is found out to be 2s plus 1, that is 2 into 1 plus 1, that is found out to be 3, and therefore these two orientations are called as the triplet state. So, now we have understood the two different orientations or two different states the electrons can be occupying. The first one is a singlet state and the second one is triplet state. So, now that we have understood about the singlet and the triplet state of the electrons, we need to now understand what is the Jablonski diagram. Jablonski diagram was proposed by Alexander Jablonski, and in this diagrammatic representation, we can understand the electronic states of the molecule and also the transition that takes place between them, along with the different kinds of phenomena that is accompanied along with this processes. So, let us take an electron. In the ground state, let us assume that the electron is occupying in this direction or in this orientation, and because the electrons are in this orientation, the spin is found out to be singlet, and because the electrons are in this ground state, we represent it as S0. So, that is the first energy level, and in the Jablonski diagram the energy levels are occupied or arranged in this manner. On the vertical axis it is arranged in the increasing order of energy, and on the horizontal axis it is arranged in the order of the multiplicity. So, this is the S0, that is the electrons are occupied in the ground state and that too in the singlet state, and whereas the T1 stands for the triplet state. Now, let us take the S1, that is when this electron is bombarded with a suitable frequency of light, that is suitable radiation h nu. This electron, one of the electron gets the suitable amount of energy and it goes from this ground state to the next excited state, but we have to remember this fact that there is no change in the orientation or there is no change in the spin of this electron while moving from the S0 to S1. That is, one of the electrons, mainly this electron, it jumps from the ground state, that is the singlet ground state, into the next higher excited state, that is in the same orientation, that is in this direction, and therefore we can say that there is change in the energy, but there is no change in the spin multiplicity of the electron while going from the ground state into the excited state. Now, let us assume the next possibility. During the next possibility, we have the electron that is in the ground state and also that is in the S0 state, or we can say that the electron is present in the ground state in the singlet orientation or singlet state. And now, when a suitable radiation, that is h nu, is bombarded onto this particular state, the next orientation or next possibility is that while this particular electron, that is while this particular electron, when it goes from the ground state, that is S0 ground state, to the higher state, that is the excited state, on moving from this state to the next excited state, the electron, the spin or the orientation of this electron is reversed or it is changed during this transition. And so, this particular, which is occupied in the upward direction, while going from this state to the next excited state, there is a change in the spin of this electron. So, basically there is a change in the spin as well as change in the energy of this particular electron, and therefore we can say that this is represented as T1 or the excited triplet state. Now, let us consider which one is more stable, that is the corresponding singlet state or the corresponding triplet state, which one is more stable? The answer is this triplet state. We can see from the diagram, comparing S1 and T1, S1 is having higher energy when compared to T1 because the S1, that is when the electrons are given the maximum multiplicity, it is of lower energy, or it is, we can say that it is more stable when compared to the singlet state. So, this is very much understood from the Hund's rule of maximum multiplicity. When we have 3 electrons and the 3 electrons are occupying in the p orbital, we arrange the p electrons in this manner, that is we are giving it maximum multiplicity rather than arranging the electrons in this manner. That is, this is the correct way where we represent the electronic configuration of 3 electrons in the p orbital rather than this method. So, from this itself we can understand that when the electrons are given maximum multiplicity, it is of high stability, or we can say that it is of lower energy. Let us consider we have a pair of electron and it is occupied in the ground state, and because the spin multiplicity is found out to be singlet, it is occupying in the S0 state. Now, I am applying a suitable radiation, that is H nu. This electron can occupy this position, that is in the S1 state. It goes from the ground state to the next excited state S1. There is also a chance that this electron can be occupying in the S2 or S3 or S4 state depending upon the amount of energy. So, for our understanding or for making this concept a little easier, we are basically just concerning about S1 and S2 state. So, in this state is not that stable, and so this electron after a very short span of time it comes back into its original state. So, when it comes back into the original state, there are two chances. The first one is a non-radiative process, which we call as internal conversion. Internal conversion is the process in which the electron comes back from the excited state to the ground state, and it can be a non-radiative process or it can be a radiative process, and for both these cases we generally call it as internal conversion. And now this is called a non-radiative process. And another possibility is that the electron can come from the excited state, that is from the S1 state to the S0 state, with the dissipation of the extra amount of energy in the form of light or in the form of radiation, and that is called a radiative process. This radiative process is called as fluorescence. So, internal conversions can be a radiative process or as a non-radiative process, that is the electron jumps from the excited state or comes back from the excited state to the ground state, and it occupies the same multiplicity, and if it is a non-radiative process it can be either in the form of heat, but whereas if it is a radiative process, that is very much called as the fluorescence phenomenon. Okay. Another possibility is that the excited singlet state, that is S1, from the S1 this electron can be within a very short span of time, there is a possibility that it can occupy or it can change its orientation and be in the excited triplet state. So, basically we can say that when the electron is converted from a singlet state to its corresponding triplet state, we say the process to be as inter-system crossing. Inter-system crossing is when the electrons jumps from or goes from the singlet state to the corresponding triplet state. That process is called as inter-system crossing. When compared to the S1 and the T1, we said that T1 is highly stable, comparatively stable when compared to the S1. So, at this process the electron will be occupying in the triplet state for a comparatively larger amount of time compared to the S1 state. So, after a little time, after a short span of time, the electron can be come down in the form of a radiative process or in the form of a non-radiative process. If it is a radiative process, we say that it is called as phosphorescence. Let us see the difference between fluorescence and phosphorescence. In fluorescence and phosphorescence are both radiative process. The major difference between fluorescence and phosphorescence is that in phosphorescence the electrons changes from the triplet state, that is the excited triplet state, to the ground singlet state with the emission of light, and this process is called as phosphorescence, whereas fluorescence is also a radiative process where the electron jumps from the excited singlet state to the ground singlet state with the emission of light, and this is called as fluorescence. So, in this Jablonski diagram we have discussed some important terminologies. The first one is fluorescence, we have discussed about phosphorescence, we have also discussed about intersystem crossing and also about internal conversion. So, internal conversion is basically when the electrons jumps from the excited singlet state to the ground singlet state. It can be either a radiative process or it can be a non-radiative process. If it is a radiative process, it is called as fluorescence, whereas in phosphorescence we say that the electron from the excited singlet state is not that stable, and within a very short span of time this orientation of this electron is changed and it goes back into the triplet state. This triplet state, the electrons can be occupying for a little more span of time or little more time, and after some time this electron goes back into the ground singlet state. Going back into the ground singlet state, it can be a radiative process, and that radiative process is called as phosphorescence. I hope you understood about the Jablonski diagram and the different aspects of photochemistry. Thank you and have a nice day.